Okay. So we were taking the examples. Now I'm taking example of iron H2O whole 6, and the second example that I will take is iron CN6 4 minus. Now first example, you see how are we going to get about the whole information. Iron in water, firstly, because water is not having any charge, so iron is in +2 state. X plus 0 is equals to +2 that we just calculated. Iron in +2 is 3d6, right? When 3d6 is there in the octahedral environment, firstly we need to ask whether delta EQ will be there or not. For this, whether electric field gradient is there or not. And for this particular thing, we need to see whether lattice contribution, valence contribution is there or not. For example, if I am firstly taking, we will draw this D6, 3D6. We know the splitting. Why I do like this? Why not pairing at the end? Because H2O is a weak field ligand. It will cause the high spin. High spin means firstly all the electrons will go to all orbitals, then the pairing will start. So that's why sixth electron comes over here. Is this clear?
Clear, ma'am.
Similarly, if I take the simultaneously this, X, Cn is having negative charge, 6 Cn will give you -6, outside it is -4. If I'll send the 6 over there, it becomes 6 minus 4, that is 2. That means iron here also in +2, that is 3d6. But here you need to see ligand is Cn. Cn is acceptor ligand, which is a strong ligand. And strong ligand makes a low spin complex. So therefore here 3d6 would be all the electrons would be filled in the same T2G orbitals and it will not go to EG orbitals. So is this clear?
Clear, ma'am.
Okay. Now I will just take this 3d6 over here. And here the 3d6. Okay. So here we were having iron H2O whole 6 2 positive. Here iron Cn whole 6 4 negative. Now for the firstly we will see the lattice contribution. Lattice contribution, if I say that all the ligands are water only, so firstly we will say it is having what kind of geometry? That is octahedral geometry, right? All are having metal ligand in this particular form. So all are same and they are having octahedral geometry. True? When octahedral geometry is there, you might have heard about some effect called John-Toller distortion. Are you aware of this particular terminology?
I know, ma'am. John-Toller distortion, I know.
Okay. So whenever we have any higher symmetry, that means octahedral symmetry is there. Because of this distortion, it tries to reduce the symmetry to lower level. For example, we saw in group theory, octahedral can go to lower symmetry of C4V, D4H, these kind of symmetry. That means square planar, tetrahedral or something like that, tetragonal. So these kind of symmetry. So because of the John-Toller distortion, it happens from one symmetry to other symmetry. What happens here? When we have a metal in this particular form, the ligand, this side we call as axial ligands, and in the plane we call them as equatorial ligands, right? So whenever John-Toller distortion is there, what happens? Either these ligands on the axial sides, they expand or they contract. Because of this, their shape does not remain octahedral anymore. When I'm expanding, at the time, they both will go out, or if I'm contracting, they will come more closer to the metal. There, all that time also, octahedral does not remain the octahedral anymore. it will either go to the tetragonal, and later on both the ligands at the axial position they get removed, and we ended up having only 4 ligands, that is making square pennant. So we are coming from a very higher symmetry to the lower symmetry to maintain the energy, right? So this kind of things we will observe in Jahn-Teller distortion. But what are the factors that affect the Jahn-Teller distortion? I am not going for the full details. You can go back and just read about it. Jahn-Teller distortion happens when there is unsymmetrical filling of d electrons in T2G and EG orbital. Mostly if there is unsymmetrical EG, that will be having high Jahn-Teller effect. If it is T2G, then it would be having weak Jahn-Teller, but it would be there. But if at all it is symmetrical, so if at all we have symmetrical filling of the electrons, say for example, if I have T2G6 EG0, or if I have T2G3 EG5, right? And maximum if it is T2G6 EG4. So these particular cases where my electrons are being filled exactly similar in the particular same energy orbitals, or if it is like splitting occurs, but both or all of them are same, and if it is completely filled. So this kind of symmetrical, they have no Jahn-Teller distortion, first case. And also no Jahn-Teller distortion will occur if it is not having an octahedral symmetry. So that factor also you have to keep in mind. If at all there is no octahedral symmetry, you do not even think about the Jahn-Teller distortion. Second case, now when we talk about this Jahn-Teller distortion, I am having iron in +2 that we saw high spin, iron in +2 that we saw in low spin in case of water as a ligand, in case of CN as a ligand. Now here T2G6, here we would be having D6 and it would be splitting as D6 would split as this one. Now you tell me in this particular case whether Jahn-Teller distortion will occur or not.
Jahn-Teller distortion occur.
Why is it so? Because it is unsymmetrical filling, right?
Unsymmetrical.
Here is one extra electron that has made this particular orbital filling as unsymmetrical. Since it is unsymmetrical, therefore it is having Jahn-Teller distortion, right? Here in D2, in this particular case, when there is low spin, all are filled like this way. Now, is it symmetrical or unsymmetrical?
Symmetrical, ma'am. Jahn-Teller distortion not occurred in symmetrical region.
Okay. So this is clear now. So what we got to know about that iron water case, why are we looking at these aspects? We were firstly talking about the lattice contribution, right? The lattice contribution has to come from the environment, what we are having around the metal. Since ligands are all same, so it should not be having lattice contribution. But it due to the Jahn-Teller distortion, now it is having lattice contribution. Though it is weak, but it is there. It is clear?
Clear, ma'am.
In case of iron CN, here, because of the same CN ligand, there is expected to be no lattice contribution, and also there is no Jahn-Teller distortion. So ultimately, lattice contribution is 0. This is clear?
Clear, ma'am.
Now we are coming to valence contribution. Valence contribution says there should be unsymmetry filling in the electrons. So we have seen that it was like this particular way, T2G4 EG2, and it was symmetrically filled like this, T2G6 EG0. Now, which one is going to have valence contribution?
T2G4 EG2, ma'am.
Why is it so? Because this is unsymmetrical filling. This is
Unsymmetrical.
so this is having valence contribution. This is not having valence contribution. Now you saw that in case of iron water, and iron CN6. We will now take all the points into consideration. First, you see that oxidation state is constant for both the cases. This is 4 negative, sorry. Oxidation state is +2 for both the cases, right? So we can compare the isomer shift also for both the cases because there are only high spin and low spin difference. This complex is high spin and this is low spin. Clear?
Clear, ma'am.
Which one is going to have more negative delta value, more towards left side, as per what we studied?
Fe2 plus high spin goes to more negative, ma'am.
Think about it again. Which one is having less d electrons?
Less d electrons. FeCN6 because most of the electron taken by Cn from d orbital of Fe.
Yeah. So that even though d6 are there in both the cases, but because of this low spin, that Cn being acceptor ligand, that would be having less strength of d electrons, that will give you more s electron penetration. So that is going to have more delta negative. So we just read no that if higher the oxidation state and low spin complexes are going to give you more negative d value. That is clear now?
Clear, ma'am.
Right? So if I am having this delta value, say for example here, so earlier I saw this kind of peak here. So this also like this thing. Right? So here, say for example, it has to go to the, this is more negative value compared to the other one. That means it is towards the negative value and this is towards the positive value. Say for example, it is X and it is delta equals to Y. We are not comparing, but we are just saying delta Y is more negative compared to the X. True that? Now, we saw lattice contribution, valence contribution. So delta EQ. Lattice contribution is there in case of iron water because of the John Turner.
Yes, ma'am.
Right? Because we saw the splitting to be like this way. Because of this unsymmetrical filling of T2G, it gives us weak John Turner distortion and therefore lattice contribution exists. Now valence contribution, it is there in this one.
Valence contribution occurred, ma'am.
It is
Valence contribution occurred in FeH2O6.
right. So it, both the factors are there. So these both the factors will give me electric field gradient. That means it is non-zero. Therefore, there would be splitting of the peaks that will exist. Now, this particular peak will split into this particular peak. The dashed one is now actual spectra for my iron aqua. And this is having this difference of delta EQ, that quadruple splitting. And these delta 1 and delta 2, delta 1 plus delta 2 divided by 2 is going to give me the actual isomer shift value. And the delta EQ value can be calculated by delta 1 minus delta 2. So is this clear? How we combine both the isomer shift and the quadruple splitting factors?
Okay, ma'am, I clear.
So this dashed one is your now original spectra. This way you are going to see for the iron aqua. Now come to the second case. Here we asked, okay, earlier we saw, okay, we found that delta value has to be negative. So the next question, whether these things occur or not. So was it having lattice contribution?
Lattice contribution occurred.
Does it? Firstly, you need to solve for lattice contribution, whether the ligands are same or not. If they are same, that means lattice contribution is not going to be there because there is no difference. For any contribution to occur, there will have to be some unsymmetry. If all the ligands are same, there won't be any symmetry. So first thing is gone. Second, do see whether there is jaunt or a distortion or not. So in
Okay, ma'am. Okay. Okay, ma'am. In the FeCN6 complex, same ligand, but John-Teller distortion not occurred.
So there is no jaunt or distortion,
So
no lattice.
no John-Teller distortion.
Right? Now, what about the
So
valence
automatically not available. So now, so automatically lattice contribution is not available in this complex.
Right. What about the valence contribution? Now, valence contribution is also related in the similar pattern. You need to see whether the unsymmetry filling is there or not.
In this complex, in T2G level and EG level, the electrons are paired in a symmetrical.
Right.
So there is no valency contribution occurred.
Yeah, it is filled like this way. That's why valence contribution is also there. So do you think that if both the parameters are absent, whether splitting of that one peak will happen or not?
Once again, ma'am.
See, both the parameters are absent, right? So whether first electric field gradient is there, is it existing or it is not there?
Electric field gradient is not occurred, ma'am.
Yeah, so it is 0.
Equal to 0.
So this factor is 0. Once this factor is 0, there is no point of asking whether delta EQ would be there. Delta EQ is nothing but the splitting difference. So that is also 0. So there won't be any splitting of this particular peak. This peak will come as this one peak only. No splitting. Okay.
Okay, ma'am.
So all these parameters are clear now. Like I've tried my level best to make you understand. I hope this is clear. Is there any doubt? We will just make a summary right now and then we'll take up the question because it is already 8:38. Okay. So quickly we will just see what is the summary that we have seen so far. So today we talked about the isomeric shift and we understood this delta value is dependent mainly on, I will write a proportional sign because there are some constants also. So it is mainly dependent on this S electron density penetration and the delta R value. So we found the delta R negative is always negative for the iron case, for any iron sample. So this thing you have to keep in mind. Therefore, delta value that would be negative, relatively negative, right? When we are talking about the S electron penetration, so there are two cases. If I have higher oxidation state, that would be having less d electrons, therefore more negative delta. If I am having low spin complexes, that means strong ligands are connected with my metals, that would be having less d electrons strength because they are taking from the metal, therefore more negative delta. This is clear. First factor, we just summarized it.
Clear, ma'am.
Now, second that we talked about is we talked about the quadrupole splitting or quadrupole movement that only appears when nucleus is having I greater than half. That is, it has to be non-spherical in nature. Third factor we got that electric field gradient, which will create the delta EQ, that means splitting will happen. That depends upon lattice contribution and valence contribution, which means if the ligands are all same, that time there won't be any lattice contribution. Second, we need to see whether there is any Jahn-Teller distortion or not. Here we need to see unsymmetrical filling of the d electrons. So then valence contribution would be there. If we have lattice contribution and valence contribution is there. So this case, if both are active, the splitting would be very strong. So EFG would be very strong. That means more delta EQ difference. If it is one factor is there, other is not there, then it is weak. So it is less. If other way around, if we have this is not there, this is there, that time also it is weak, that is less. And ultimately, if both are not there, this the EFG is not existing. Therefore, it is 0. So no splitting. In all these cases, splitting of the peak appears. In this particular case, no splitting. Is this clear?
Clear, ma'am.
All of
Clear,
it?
ma'am.
Okay. So we have, I think, covered all the topics for this particular week. I hope you have understood it well. Now we will quickly take up the questions and then we'll just start. I think we have covered a lot of things. Okay. So now you have to use your concepts very well. Now, out of iron in +2, this has been written as an oxidation state, and iron in +3. Which one is having more shielding effect? So I'll just give you a hint. When you have been given iron in +2, iron in +3, that means they are not talking about high spin or low spin. So general case. So you consider both of them are in same, either both of them would be in high spin or low spin, that you do not need to consider. When it is being asked for the shielding effect comes from the d electrons. So now you need to see which one is having more number of d electrons. That would be going to give you more shielding effect. More the d electrons, that will shield the s electrons to go into a nucleus. So which one is going to show more shielding effect? That is the question. Because concept is same, but the questions could be framed in different manner. Sometimes it would be asked in terms of isomeric shift, which is having more negative value, which is having less value. But sometimes it would be about the more number of d electrons or directly about the shielding effect. So now you need to tell me, out of iron in +2 and +3, which one is having more shielding effect?
Fe +2, ma'am. More shielding effect because it contains more number of d electrons compared than Fe +3.
So how many d electrons are there in Fe2?
Fe2 d6.
Yeah. So it is 3d6. This is 3d5. Since d electrons are more, so iron 2+ is having more shielding effect. This question is clear?
Clear, ma'am.
Oh. Now come to the next question. We have covered this question. Isomeric shift. Okay. Now isomeric shift is relatively more positive. Till now we were talking about more negative, now more positive when the oxidation state is constant. So we have kept the constant oxidation state at constant. We need to talk about delta value would be more positive for what? Either it has to be high spin complexes, B option low spin complexes, pi acceptor ligands, or donor ligands. It is the reverse what we just said. We said isomeric shift is dependent upon the spin states, different types of ligands. We were talking about more negative. Now you have to reverse the situation. I'm asking for more positive. So tell me about isomeric shift is more negative or which high spin or low spin? Acha.
More positive.
So think about strong field ligand, matlab accepting ligands. They are going to give more D strength or less D strength.
Low spin complexes, ma'am, because in low spin complexes, it is a strong ligand. So D electron, number of D electrons is lesser.
That will be having lesser. So more negative will come from low spin as well as strong field ligands. That is the ideology, right?
Okay, ma'am.
Right. So I am asking about more positive. So which should be the answers? It's just
High spin complexes, ma'am.
and you need to see all the points. There could be possible that one is the answer or there are multiple answers. That is right, high spin complexes. And is there any other option?
High acceptor ligands.
Think about it again.
Ma'am, pi acceptor ligands means the electrons are getting from the metal to ligand, I think.
Yeah, right.
D option, pi or sigma donor ligands means
Yeah,
I
that is
cannot
right. You have
understand.
to be confident because see, the concept is clear. You need to understand the concept regarding the d electrons. Firstly, d electrons, if they are more, then delta value is less, negative. That means more positive. Okay? If d electrons would be more, then they will not let the s electrons to go into the nucleus. When that is not happening, the delta value becomes less negative, which is more positive. How the d electrons could be increased when we have high spin complexes? How it is high spin complexes when we have weak or donor ligands? That's what I was asking. How do we get the more positive value? How do we get the more positive value when we have high spin complexes as well as donor ligands? So now it is clear. The questions can be twisted. Maybe we are looking at more negative value. I'm asking for more positive. That means towards the right side. So which one is going to have that one? See, for example, if I have iron with water complex and iron with CN complex, just now this example we saw. Which one is having more positive value, delta? Think and use this concept now.
FeCN6 is more positive, ma'am. More negative.
Yeah. Why more negative? I am asking about more positive. Now tell me why more positive for iron aqua?
Pardon, ma'am?
Why more positive value for iron aqua?
Yes, ma'am. Iron aqua more positive.
Yeah, why?
Because it is unsymmetrical distributions of the T2G and EG.
Okay, but right now I'm just talking about the unsymmetry we will see or we will consider only when we are talking about the splitting. I'm just asking for the isomeric shift, that single peak. Isomeric shift is dependent on what? Firstly, the oxidation state. Second is the high spin on low spin. So you need to define the answer in terms of that only. Splitting is also fine. That will come under, or unsymmetrical filling will come when we are talking about that quadruple splitting. Firstly, you tell me which one is high spin, which one is low spin.
Yeah, FeH2O6 is a high spin because it contains weak ligand.
Right. So it is high spin,
FeCN6
and this is weak ligand. So that's why it is
weak
having
ligand.
delta value more positive. That means it would be towards the right side. So that
Right
was the
side,
only
more
question
positive.
about the isomeric shift. Now you understood with the example, like what we were talking about.
Okay, ma'am.
Now try the next question is also same. Isomeric shift is relatively more negative for You have been given 4 options: iron +1, +2, +3, +4. Which one is going to give you more negative value?
Fe plus 4, ma'am.
Why is it so? Why iron +4 is having more negative value?
More negative because number of d electron is less
Right.
compared than other iron.
More oxidation state, less d electrons, then more s electron density on the nucleus, and therefore more delta negative. Now it is clear?
Clear, ma'am.
Moving towards the question number 4. Isomeric shift is due to what? Is this shielding effect of s electrons on d electrons only? Shielding effect, just read it very carefully. Which one is causing shielding effect on what? Shielding effect of d electrons on s electrons only? De-shielding of d electrons on s electrons, or shielding effect of p, d, f electrons on s electrons? This is in case of I'm asking about the general. This is
B
general.
option, ma'am. Shielding effect of d electrons on s electron only.
Okay. So this I understood why you said it, because it was in case of iron. We said that P is constant, so that's why it is not affecting. But actually the general and the right definition is shielding effect of PDF electrons on S electrons. If you understand from last lecture that we were making the radial function graph, right? So there we specifically said that P, D, F electrons, they shield the S electrons from the nucleus. In case of iron, I understand that we said 3s2, 3p6, 3d6. So the 3p6, whatever it is causing, the shielding effect, that is constant for every iron metal source. But actually it is there. It is cancelling out because we are talking about the relative thing. For example, if it is giving a shielding effect of X, and this is giving a shielding effect of X1, Y1. In case of iron +2. Iron +3 may, the X1 is constant, but Y1 has been changed to Y2. But still we can't ignore that it is giving some shielding effect. Right? So the total shielding effect is X1 plus Y1. And in iron +3, it's X2 plus Y2. It's X1 plus Y1. Right? So if I'll just cancel out this effect, I'll remove X1, X1. So ultimately it depends upon the d electrons. But we cannot ignore that p electrons, whatever they are in the valence shell, they are also participating in shielding. But in all the complexes, it is constant. That's why we said that it is not affecting more. But we cannot ignore that both p and d electrons and if f electrons if existing, then they are actually shielding your s electrons from the nucleus. Clear or not?
Clear, ma'am. Okay, ma'am. I understood.
Okay. Say, for example, if you'll see the tin, no, if you just take the tin and the valence shell electron, that is having S and P. The d electrons, the d10, that would be constant for every tin material. There we will be talking about p electrons over the d electrons. You're understanding, but actually it is the PDF, all the orbitals, they are screening or they are shielding the s electron from the nucleus. So the general, when it is talking about, that is coming from every PDF electron. Clear?
Clear, ma'am.
Okay. Now try the next question. The quadrupole effect. We saw that quadrupole effect like this way, where the charges were like this way. So it occurs for what? It is possible when I is greater than half. B option, I is equals to 0 or half. C option, it is spherical nucleus. D option, it is non-spherical nucleus.
I greater than 1/2. That is the first option, A.
Yeah.
And the next option, D also correct, non-spherical nucleus.
Good. Very good. Now try the sixth one. For electrical free field gradient to exist, the condition or conditions are, there could be one option, there could be many options. See the options, whether it requires inhomogeneous electric field, whether it requires spherical nucleus, homogeneous electric field, non-spherical nucleus. We had that 4 cases, right?
In yes, ma'am. Yes, ma'am. Okay. A option in homogeneous electrical field and also non-spherical nucleus.
Great. So I think you have understood the concept really well now. So it's A and D option. Here also it's A and D. Here it is D option. So it is right now. We can move to next questions. So try this one now. For complexes A, that is A equals to iron CN6 2 positive. Sorry, this is 2 positive, and iron, just a second. There's some mistake in the oxidation state, I guess. So here it is. Four negative, and here it is 3 negative. Okay, you just try now. If I am having sorry for the inconvenience. Okay, so now just try this way. So if I'm having, I don't know whether it is iron CN6 4 negative and iron CN6 3 negative. Now you need to find out which statements are true. You need to find out the isomeric shift is more negative for which one, or more positive for which one, and whether electric field gradient is existing for both A and B, or it is existing only for B, not A. I know this is bit tricky and bit lengthy, but just take one by one the concept. I will give you one example here itself. So we will firstly talk about the isomeric shift. So first, for isomeric shift, we need to see the oxidation state and the spin. What do you think? Both would be in same spin or different spin? Both will make high spin or low spin complexes, or it would be different?
Both are same, ma'am, same ligand,
And ligand is strong or weak?
strong ligand.
So it will make high spin or low spin?
Strong ligand, low spin, ma'am.
So both are low spin. So one condition is fixed,
Both are low spin.
right? Now see the oxidation state. How do we calculate the oxidation state? Consider the oxidation state of metal as X. Cn will give you minus charge. It is -6, and outside it is -4. Therefore, X becomes +2. Here also, यहाँ पर X
Plus 3.
-6 -3, X equals to +3. Therefore, iron is in +3, right? Now, which one is going to have more negative? Just read the A and B statement and let me know which one is true.
More negative. The FeCN6 is more negative, ma'am.
F in C, which one?
Uh,
4 minus
Fe
A
plus
or
3.
B?
Fe plus 3 oxidation state. Fe plus 3 oxidation state having more negative.
So if it is
More negative isomer shift.
is there any option of more negative for B?